let's go ahead and get started. Hopefully the first question is pretty darn easy. Thank you. What is point slope form of a linear equation? Everybody raise their hand and tell us what that is. It's all the way back in algebra. Okay, y equals mx supposed to be a slope-intercept form. If we want point slope form, it's y minus y1 equals mx minus x1. Okay, and remember the formula for slope is it's the difference in the y's. Okay, so this would be y2 minus y1 over x2 minus x1. So if I wanted to take this right here and I wanted to plug it in right there, I could make that a really nasty looking equation. But that's if you just had an x1, a y1, an x2, and a y2, you could plug it into a formula like that, and that would be the answer there. We've done a problem like this before. Does anybody recognize this? Okay, this is an inverse trig function. That means this has got to be a ratio. That means this is going to be an angle, and the end result of this is going to be a ratio, right? So let's draw a picture of what this looks like. Let's see, if I have a sine ratio of x over 7, that's opposite over hypotenuse, right? So the opposite is x and the hypotenuse is 7. I can figure out what this side is right here by using the Pythagorean Theorem. So this is going to be the square root of 49 minus x squared. Is that okay? So I want the cosine of this picture right here. Here's the angle. We don't really care what the angle is. We just want to know what the cosine ratio is for that particular picture there. And what would the cosine ratio be? Square root of 49 minus x squared all over the hypotenuse, which is 7. So there's the answer right there. Okay, are there any questions there? Okay, you want the light on or off? Off? Well, stay awake. Okay, so these are just kind of a lead-in. We're actually going to use these ideas in just a second. This section is on something called parametric equations. You've seen these before. It's another thing that we get introduced into in Math 1060 that we're going to use a little bit in this section, but if you go on in math, these are actually used fairly extensively because they can model motion and different things like that really effectively. Parametric equations can do things that regular Cartesian equations or rectangular equations, the stuff that you're very familiar with graphing, they can't do, okay? So what we want to do is first of all talk about what a parameter is. A parameter is a determining factor, or it's a constraint of a problem. It's what decides what goes on. And when we're solving a problem, it's sometimes useful to break it into little parts. Solve this piece, then solve this piece. And if we're dealing with vectors, for example, it was helpful to break them into a horizontal component and a vertical component. And you can kind of treat those two things separately. So when we deal with parametric equations, what we're allowed to do is we're allowed to separate the motion or the changes in x and the changes in y and keep those completely separate. Okay, but in order to do that, we've got to introduce a parameter or some outside determining variable, and usually that's the variable t. So we're going to look at curves or graphs that have been parameterized, and when you parameterize a curve, you need three things. You need an equation for x. So you need an equation that tells you what the x-coordinate is. You need an equation for y, again, an equation that tells you what the y-coordinate is. And you need an interval for the parameter. Okay? Now, usually we use the variable t for the parameter, so we're going to call this a t interval. So you're going to need an equation for x, an equation for y, and a t interval. So we're going to do a couple of examples right here. If you haven't graphed parametric curves, we're going to start with a very simple example right here. Here are the parametric equations. You'll notice that we've got the three things that we were just talking about. I've got an equation for an equation for x in terms of t, an equation for y in terms of t, and then I've got a t interval. So these are the values of t that are okay to plug into both of these equations. Okay, so this is the parameter. This is what's going to determine what goes on here. So here's how it's going to work. I'm going to have Caitlin here. She's going to be the parameter t. All right. We're going to have Kahala. She's going to be the x. And let's go back there with Skylar. Skylar's going to be y. Okay. So Caitlin's t, Kahala's x, and Skylar's going to be y. Now, who's in charge of this whole situation here? Caitlin is, right? Because Kahala and Skylar can't figure out what coordinate they're going to say, what the x coordinate is and what the y coordinate is, until she says what the t is. Now, if you'd be kind about this, you need to pick numbers that are in between -4 and 4, endpoints included. We probably ought to go about it in a nice organized fashion and pick numbers that are pretty easy for them to plug in. So what would be the nice, easy number to pick first? 0. Okay, let's pick 0. I'm going to put 0 right here. Now, the minute Caitlin says 0, Kahala's thinking, well, hey, I've got to figure out what the x coordinate is. So she plugs a 0 in here, and what's your answer? -4. Okay, and Skylar, you plugged a 0 in here, and what do you get? You get a 1. Okay, what do you want to pick next? Okay, so we'll pick -1. I'm going to put it right there. The minute she says -1, Kahala plugs that into the x equation, and what do you get? -6. And Skylar's going to plug in a -1, and what do you get? You get a 0. Okay, next.
4.
She wants to plug in a 4. Okay, I'm going to put a 4 down here. She says 4. Kahala thinks 4. Skylar? 5. Okay, now, do you get the idea? Okay, the parameter is what determines what goes on here. Okay, without the parameter, you can't do anything with the x and y. So we're going to plug these numbers in, 0, 1, 2, and 3. Let's figure out what goes on here. If I plug in a 1 into the x, I get a -2. If I plug a 1 in here, I get a 2. Now we can kind of notice a pattern here. What's happening with the x's? They're getting bigger by 2 every time, right? So this next one is going to be 0, and this would be 2. Let's just double check and make sure that one's right. If I plug in a 3, I get 6 minus 4. That's going to be a 2. This one looks like it's adding 1 every time, so this is going to be 3, and this is going to be 4. Again, let's check this one right here. If I plug a 3 in, I do get 4. Now, here's the interesting part about this. We came up with some points that we're going to graph. They were all determined by t, but t doesn't actually get put on the graph. This is an xy pair, that's an xy pair, that's an xy pair. I've got 6 xy pairs here. Now, these are the nice numbers that we could plug in for t. There's no reason other than we told Caitlin not to pick radical 2, okay, because that wouldn't be any fun to plug in, or 5/2 or something like that. Those would still be in the interval, but they'd just be a bit of a pain in the butt to graph those, okay? So let's come over here and let's sketch these. And it says, graph the following parametric equations, indicate the orientation. Okay, here's what orientation is. Orientation is the direction of travel. So we're going to start at the first t value, and you can kind of think of t as time. So we plugged in a -1, and we got this point, -6, 0. So at t equals -1, we were right here. Then when t was equal to 0, we were -4 and 1, so about right here. So that's when t equals 0. I've got another point at -2, 2, so back 2 and up 2, so right here. And that was when t equals 1. Get the idea? Okay, I'll do one more in color, and that's going to be 0, 3, so we're right here. And that one was when t equals 2. And then I get to finish up when t equals 4. I'm at 4, 5. So 4 and 5. So like this. And that happened when t equals 4. Now, we started out right here and we ended up right here. So we're going to go from here to here. And I'm going to put arrows on here because that indicates it started right here and it ended right here. So on this particular one, this is the initial point, and this is the ending point. That would be the terminal point there. Any questions?
Would you still put an arrow on the end then? That's the
The arrow just so I'll put it right there so it's not right on the end. It doesn't continue going on forever. It stops, or it starts here and it stops right there. Now, if we had said, so this is a good point to make, if we had said t has to be greater than or equal to -1, then we just continue going on. Okay, it would have started right here and continued going in that direction. Or if we said this, what if we said t is less than or equal to 4? Yeah, then it would have gone the other way. Any questions? Okay. All right. Let's look at this one. This is a good problem, a little bit more complicated. Again, we've got a parameterized curve. We've got an equation for x, an equation for y, and a t interval. You'll notice this time t starts at -2, and then you can plug in any number you want that's bigger than or equal to -2. So let's start by plugging in a -2, and then we'll plug in a -1 and a 0 and a 1 and a 2 and a 3, and let's see what we get when we plug these in. So you can do these an x then a y, or you can do all the x's and then a y. So let's plug this in. Let's plug it into the x. If I plug in a -2, I get a -3. If I plug in a -1, I get a -2. If I plug in a 0, I get a -1. Okay, what I'd like you to take a look at is, notice that this one's going to change. It's going to go up by 1 every single time. Okay, that's what we call changing in a linear fashion. It's kind of like this is a little linear equation, just like that was a linear equation and that was a linear equation. The y's went up by 1. Notice what the slope would be here. You watching? See what the slope would be here? The slope would be 1, so it would increase by 1. What would the slope for the x's, or the rate of change for the x's, be? It would be a 2, so it's going up by 2 every single time. Okay, now, what if I change this to a -2? What do you think would happen with the x's? Yeah, they'd get smaller by 2 every single time. Okay? But it is changing in a linear fashion, so this one's pretty darn easy to keep track of. This one's going to be a 0, this is a 1, and this is a 2. And let's figure out what the y's are that go in here. So if I plug in a -2, I square that, that's 4, add 1, so I get a 5. Plug in a -1, square that, I get a 1, add 1, I get 2. 0 squared plus 1 would be 1. 1 squared plus 1 would be 2. 2 squared plus 1 would be 5. Okay, and kind of notice that pattern. Maybe that looks familiar. If I plug in a 3, I square that and add 1, I get a 10. And these are the points that we're going to graph. So even though t determines what goes on here, these are the points we're going to graph. So we'll slide over here, and we're going to graph -3, 5. So we'd be right here. This is our starting point. That's our initial point. And then -2, 2. -1, 1. Let's see, 0, 2, 1, 5, and 2, 10. Now it started here and it went like this, so when I draw this graph I can include the orientation. I'm going to put an arrow on the end there. So it came down here, like this, like this, like this. There's the orientation. Okay, are there any questions? Does this look familiar? What is it? It's a parabola, okay? It is a parabola. It's not the whole parabola though, is it? Nope. And that's the interesting part about parametrics. You can create the same shapes that we can make in rectangular form, but we can just make parts of them. Just like up here, this is just a line, we just had part of a line. So we have a lot of control over the shape, where it starts, where it stops, how we create it, and that sort of thing. Okay, so let's take a look at the next part here. Occasionally, if you look at a parametric equation, you can tell what the graph is going to look like. But it's actually pretty tough to do that. Most of the time, you look at a parametric equation and you've got to actually sketch the graph or have your calculator do some work before you could tell what it looks like. So what's sometimes helpful to do is change this into rectangular form. Change from x's, y's, and t's to just plain old x's and y's. Okay? And that's called eliminating the parameter. Okay? So if we're going to eliminate the parameter, occasionally we'll get lucky, but most of the time we have to go through this two-step process. So the two-step process is this. Solve one of the parametric equations for t, and then substitute that t into another equation. So I've got 3 examples of this. 2 of them are relatively easy, and then one's a little bit uglier. Okay? So we're actually going to do A, then we're going to do C, and then we're going to look at this one because B's the worst. Okay? So this is actually the equation that we had up above in example 2. Of the x equation or the y equation, which one would be the easiest to solve for t? X would be. So I'm going to take this and I'm going to say x equals t minus 1, which means if I solve for t, I get t equals x plus 1. And then wherever there's a t, I'm going to put an x plus 1 in the other one. So I've got y equals t squared plus 1. I'm going to take this and I'm going to put it in its place. So this means y equals x plus 1 quantity squared plus 1. Okay, now what I've done here is I've gone from 2 equations, 2 parametric equations, both of which involve t, to one equation that only has x's and y's in it. That's a rectangular, or that's a Cartesian form of this particular graph. Now, take a look at this. This should look familiar, because about a year ago, most of you were in Math 1010. What shape is this? Parabola. Where's the vertex? At negative 1, 1. And look where the vertex is right here, at negative 1, 1. So does this, in rectangular form, confirm that we have the correct shape on this parametric curve? It does. But again, with the rectangular curve, it's not the entire parabola. We'd want to say, hey, we can't have an x that's less than negative 3 or something like that. Okay? So we might want to add x has to be greater than or equal to negative 3. Because it's not the whole parabola. But it does help us look at it and say, oh, I know what that looks like. Okay, let's take a look at this next one. Now, this one actually is pretty easy because we get lucky here. This says x equals tangent x, and y is equal to 7 tangent x, or tangent, sorry, did I say that right? X equals tangent t, and y equals 7 tangent t plus 4. Do you really have to solve for t on this one? No, wherever there's a tangent t, I can put an x. So I could put this right there. What would the equation be then if I replace tangent t with an x? 7x plus 4, okay? Now, if we stuck with the idea that we usually solve one of the equations for t, I'm going to take this one and I'm going to solve it for t. That means t is equal to tangent inverse of x. Then if I plug this in for t, this is what I get. I get y equals 7 times the tangent of the tangent inverse of x plus 4. And what's the tangent of tangent inverse of x? They undo each other, so you just get an x. So I get x and I get y equals 7x plus 4. So this is a really ugly form of this equation. In parametric form, it's pretty awful to look at and pretty awful to deal with, but it's just a line. Slope of 7 crosses the y-axis at 4. Okay? A lot easier to deal with rectangular form in that one than it is to deal with parametric form. Okay, any questions there? Okay, let's take a look at the next one. Okay, so on this problem right here, again, we want to eliminate the parameter. So, that's weird. Did the stuff I wrote here disappear? Eliminate the parameter and solve one of those for t. Sorry about that. That's weird. Okay. We don't need quite that big. Okay, so on this one, we want to come up with a rectangular form here. We want to eliminate the parameter. We want to get rid of the t. Usually we pick the easiest one, but there's really not an easy one to solve for t, is there? Okay, they're both about the same. Okay, before we finish this off, I want you to think about this, because occasionally they'll ask something like this on a final exam. They'll ask you to figure out what the domain is and what the range is. So domain deals with x's, so we can just look at this equation right here, and range deals with y, so we can just look at this one right here. So my question for you is, what's the biggest x and what's the smallest x that we'd ever get out of this equation right here? 7 and -7, right? Because the range for sine is from -1 to +1. So if I multiply that by 7, I'm going to get an answer between -7 and +7. What about the range? Range is y, so we'd look at the y equation. So that's going to be from -4 to 4. So we don't go outside of a little box. We can't go past -7 to the left or past +7 to the right, and we can't go above 4 or below -4. So we're in kind of a little box with whatever this equation is. Does anybody know what this is? Okay. We're going to get it into a form where you'll be able to recognize it based on what you saw in 1050. So here's what we're going to do. I'm going to take this one and I'm going to solve it for t. If I solve it for t, this is what I get. I get x over 7 equals the sine of t. And then I'm going to take the sine inverse of both sides, so I get t equals the sine inverse of x over 7. Now, once I've solved for t, I take that expression and I plug it into the other equation. Now I solved the x equation for t, so I'm going to take this and I'm going to plug it into the y equation. So I'm going to take this and it's going to go right here. So this is what I've got now. I've got y equals 4 cosine of the sine inverse of x over 7. Now, technically, have we eliminated the parameter? Are the t's gone from this problem? They are. But normally we'd want to clean this up and make this look just a little bit better. Does anybody recognize that? That was the starter question, right? So we could draw a picture of that again, but correct me if I'm wrong, this turned out to be the cosine of sine inverse of x over 7 was the square root of 49 minus x squared over 7. Is that right? That's what it was, right? Okay, so here's what we've got at this point. Y equals, I'm going to write it this way, 4/7 square root 49 minus x squared. Does anybody know what it is now? Okay? I'd be amazed if you knew what it was now. Let's square both sides. That's going to be y squared equals 16 over 49, and then this is going to be 49 minus x squared. Just to make things a little nicer, I'm going to multiply both sides by 49. So this is going to be 49 y squared equals 16 times 49, and then negative 16 x squared. Anybody know what it is now? Close. It is an ellipse. It is an ellipse. Okay, I'm going to take the negative 16x squared and move it to the other side. So this is 16x squared plus 49x squared, excuse me, 49y squared equals 16 times 49. I'm not even going to bother multiplying those together. And I'm going to divide everything by 16 times 49. And here's what I get. The 16s would cancel. I'd get x squared over 49. The 49s would cancel. I'd get y squared over 16. And then I get a 1 over here. That should look familiar. That's an ellipse. How far do you go in the x direction? 7. And remember, this would be centered at the origin. So we'd go to positive 7 and negative 7 on the x-axis. How far would we go in the y direction? Plus and minus 4, okay? So that explains that domain and range that we had here. Okay, are there any questions there? I think you've got one problem like that, okay? And I think it's very similar to that. Any questions? Okay, go ahead and flip the page over. You've got a couple problems that ask you to parameterize a curve. So what that means is take some information, maybe an equation in rectangular form, and put it in parametric form. So that means you've got to have three things. You've got to have an equation for x, you've got to have an equation for y, and you've got to have a t interval. Okay, so you've got to have an interval for the parameter. Okay, if all the instructions say are just parameterize the curve, then it's pretty darn simple. So let's say it said parameterize this. You've got to have an equation for x, an equation for y, and a t interval. Well, the easiest way to parameterize a curve is to do this. Let's say x equals t. If x equals t, then wherever there's an x, I can put a t. So this would be y equals t squared plus sine t minus 4. Now, since there are no limits on what x can be here, from negative infinity to infinity, there are no limits on what t can be, so we could say t is any real number. Okay? And if they were all that easy, it would be great. Okay, but they're not. So let's take a look at the next example. Now, your textbook shows you, let's see if I've got room here. Your textbook shows a problem like this, and they show you the easiest type, and that doesn't do you any good. We're going to do two of these problems. We're actually going to parameterize a line. So this is a line that goes from 1, 3 to 5, 8. It starts here at t equals 0 and ends here at t equals 2. So let's draw a quick sketch of what this would look like. So 1, 3 would be right here, and then 5, 8 would be right here. So it starts here and ends up there. Starts here at t equals 0 and ends here at t equals 2. Okay, now I'm going to show you two ways to do this. The textbook shows you on a problem like this. There's a very easy way to do this, but it depends on the setup for the problem. It depends on t starting out with a 0. That doesn't happen here. Okay, so I'm going to show you two ways to do this. I need an equation for x. Well, let's see. How much did x change in these 2 seconds? It started out at 1 and ended up at 5. So how much did it change? 4. Okay. Well, if we figured out what that was every second, how much did it change every second if it changed 4 over the course of 2 seconds? 2, right? So what I'm going to do is I'm going to say, well, that's 4 over 2 times t. It's kind of like a rate of change or a slope for x. It went from 1 to 5 over the course of 2 seconds. Okay, now, if I plugged in a 0, I get a 0 out of this. So this doesn't start at the right place. So what I do is I add 1 to that. I start at this value right here. So here's what this says. Start at 1 and then change 4 units every 2 seconds. So the quick way to write this would be x equals 2t plus 1. Now, the test as to whether or not this works would be, if you plug in a 0, does it start at the right place? And if you plug in a 2, does it end at the right place? So plug in a 0, what do you get? You get a 1. It starts at the right place. Plug in a 2, you get a 5. It ends at the right place. Everybody got that? Yeah. Because it started at 1. Okay. So let's make one for y. Where does it need to start? It needs to start at 3. And then we're going to figure out kind of like a slope here. How much did y change from beginning to end? It started at 3 and it ended at 8. How much is that? That's going to be 5. And how long did it take to do that? 2 seconds. So we gave it a place to start. We're having it start at 3. and it covers 5 units in 2 seconds. So this would be the right equation. Let's double check and make sure that it works. If you plug in a 0, does it start at 3? Yes. And if you plug in a 2, look how these 2's would cancel. You'd have 5 plus 3. We end up at 8. So does this work? It does. Okay, this works just fine. Okay, the problem with this is a pretty easy problem to do because this starts off at 0. Okay, now I'm going to show you a way that works regardless of how, whether it starts at 3 or 7 or negative 19 or whatever it is. What we did right here is we basically figured out a slope for x. So if I said I wanted to figure out the slope for x, it would be the difference of the x coordinates over the difference in, we divided it by 2, right? 2 is the difference in the t's, the time, right? So I'm going to do t2 minus t1. Now, if I want to set up an equation for the slope of y, what would this rate of change right here be? It's going to be y2 minus y1 over t2 minus t1. Notice the bottom is the same because they both depend on the same parameter. Any questions? Okay, now this is going to look like I'm making things way more complicated than it has to be. An equation for x would be x minus x1, the slope for the x, and then t minus t1. Now, here's x1, y1. Here's x2, y2. So I'm going to do x minus, what's x1? 1. Okay, now I've got to figure out what the slope is for x. That's this guy right here. So it would be x2, 5, minus x1, 1. t2 minus t1. What's the second time? 2. First time? 0. So look what I get here. I get 4 over 2, which is 2. And then t minus, what's the initial time? What's t1? 0. Okay, now if this works, it better give me this equation right here. And look what I get. X minus 1 equals 2t. X equals 2t plus 1. I get the right equation. And you can do the same thing with y. Okay, now, you've got a problem on your assignment. I think you've got 2. One that starts at 0 and the one that does not start at 0. Okay, let's try and do this one as if it started at 0. Let's try and do it the easy way here. So, in order to come up with an x equation, how much did x change from here to here? 5. Over how many seconds did it change? 3. So there's our slope. We'd multiply that by t. And then what we did before is we said, well, let's give it a place to start. Where should this start? Hold on. Should start at 2. If we followed the exact same process, this is what it would be, right? Does it work? It doesn't work. So if all you looked at was the example in the book, you would not be able to figure this out. You really have to rely on this right here. Okay? So here's the correct way to do it. This is x1, y1. This is t1. This is x2, y2. And this is t2. Let's figure it out using this little formula right here. So this is going to be x minus, what's the first x? 2. Okay, now I've got to figure out what's the slope for the x, or what's the difference in the x's. The difference in the x's is 7 minus 2. There's the 5 we were talking about. The difference in the times is 3. It's 6 minus 3. Now here's the trick. Up on this problem, it was a 0 for the first time. So it just turns out to be a 2t. On this one, if I do t minus, what's the starting time here? Starting time here is 3. So here's the correct formula. X minus 2. This is going to be 5 over 3, and this is t minus 3. So I get x equals 5/3 t. If I distribute through, minus 5 plus 2. The minus 5 when I distribute, the plus 2 when I move the 2 to the other side, so here's what I get. I get 5/3 t minus 3. Now, how will we know whether or not this is right? Plug it in. It better start at 2 when I plug in a 3. If I plug in a 3, 5/3 times 3 is 5, minus 3 is 2. Does it start at the right place? It does. And it better end at 7. Guess what I get when I plug in a 6? 5/3 times 6. The 3 and the 6 would cancel. That would be a 2. This would be 10 minus 3 is 7. Okay? It would be very difficult to figure that out without at least thinking of it this way. It's this adjustment right here. Think of it this way. We're adjusting the time. It used to be 0. We're adjusting it by 3. So let's quickly write down what the y one would be. The y would be y minus, what's the first y? 1. And then I need the difference in the y's. 5 minus 1 over 6 minus 3. Notice how that denominator is the same thing. And then it's going to be t minus 3. Okay? You come up with a fraction, distribute through. So we've got y minus 1. This would be 4 over 3. T minus 3. Distribute through. 4/3 t minus 4, and then I'd move that over to the other side, so that would be a plus 1, so I get y equals 4/3 t. That'd be a minus 3, right? Yeah. Interesting that they both end up being a minus 3. And let's see. That works. Okay. Any questions? Okay, that one problem is the hardest problem on the assignment. Okay, so you might need to look at that example a couple times, get that figured out. You have some that ask us to change from polar to parametric. So it's actually pretty easy to change from polar to parametric. Remember, there are 4 equations that you're going to need to have memorized for the test that allow us to change from polar to rectangular, and they are x equals r cosine theta, y equals r sine theta, x squared plus y squared equals r squared, and the last one, again, was tangent theta equals y over x, and you had to be careful with this, because if you use tangent inverse, you've got to consider the range and where you actually are on the unit circle and stuff like that. Okay? So here's what we want to do. We want to take this one and we want to change it from, right now it's in polar form. It has r's and thetas. We want to change it so it has x's, y's, and t's. Okay, the Greek letter theta, it doesn't look like it, but Greek letter theta, that's kind of like a t. It's kind of like a parameter. So here's how nice this is. I need an equation for x, right? What does this say r is? 3 cosine theta. So wherever there's an r, I'm going to put a 3 cosine theta times cosine theta. So here's the r that I plugged in. So that means x would be 3 cosine squared theta. Now, is this parameterized? Yes, it is, because it's in terms, not in terms of y. It's not y that figures out what x is. It's theta that does that. And then the same thing here. So if I did this, it would be 3 cosine theta sine theta here's an equation for x in terms of theta. Here's an equation of y in terms of theta. They're both determined by some outside determining factor, some outside variable. In this case, we call it theta. That's it. That's all there is to it. You've got a couple problems like that. Any questions there? It's literally as easy as taking whatever r is equal to and plugging it in here and then simplifying. Yeah.
How come theta can be equal to t again? Or
Well, it's not that we always have to use t as the parameter. We just have to use the same variable to determine both x and y. In this case, we chose to use theta. If you want to take these and turn them into t's, that would be just fine. Still be parameterized. Good? Okay. Last set of problems. You need to know how to do these because these come up quite often. I think we've seen these, at least parts of this before. So this is how we take model motion, and this is a very common application for parametric equations. We can figure out so if we launch something, so if we shoot a bullet, an arrow, which we're going to do in just a second, launch a hay bale, I think there's an example like this in the textbook, whatever it happens to be, but if we launch it with an initial velocity, and we use v naught for the initial velocity, and if that's in feet per second, and we launch it at that angle right there, we can actually keep track of where this object is horizontally and vertically using two separate equations. So we can use an equation for x to figure out where it is horizontally, and we can use an equation for y to figure out where it is vertically. Okay? So on this particular problem, and this is in your textbook, I think this is part of your assignment, it says an archer shoots an arrow from a height of 5 feet at an angle of inclination, so he launches it upward a little bit, of 30 degrees with an initial velocity of 300 feet per second. Write parametric equations for the path of the arrow, sketch the graph, use your calculator and adjust the t-step. We'll do that in just a second. So let's come up with the equation first of all. This is the initial velocity, this is the launch angle, and that's the parameter t. That's the time in this particular problem. So this is going to be x equals, what was the initial velocity? 300. Cosine of the launch angle. What was the launch angle? 30 degrees. We're going to get that, and we're going to times it by t. For the y, it's going to be negative 16t squared. Initial velocity, 300. Initial launch angle, 30 degrees, times t. And then sitting out on the end here is h naught. What do you think that stands for? Okay, h naught is the initial height, so that's going to be 5 feet. Okay, so again, that's h naught is how we say that. That would be the initial height. Okay, so here are the equations we're going to use. Cosine of 30 degrees. Radical 3 over 2. So this is going to be x equals, if I cancel the two of those, that's 150 radical 3 times t. Sine of 30 degrees. 1/2. So this is going to be y equals negative 16t squared plus 150t plus 5. So really, after that ugly mess, they're really not too bad. Here are the parametric equations. Have we truly parameterized this? How many things do you need to truly parameterize a curve? You need 3, right? Equation for x, done. Equation for y, got that. What else do you need? An interval, a t interval. In this case, it's really clear. It's a time interval. We started a stopwatch right when this archer launched the arrow, so this would be t greater than or equal to 0. We'd start at 0 and then go till it hits the ground or the target or whatever that happens to be. Now grab your calculator. Okay, just like yesterday, we're going to change the mode. You probably haven't used this mode before, so we're going to hit mode. We can do radians if you want, or degrees. It doesn't matter. We already took care of the degrees in this problem. I suppose you could put it in degrees and type that equation in just as it looks, and it would calculate it for you. We did a little bit of the math first. We're going to come down here. We're not going to graph in function mode or polar mode. We're going to graph in parametric mode. So we're going to hit enter on parametric. Go ahead and leave the rest all highlighted on the left-hand side. Everybody good there? Raise your hand if you've graphed on your calculator using parametric mode before. One person? Okay, let's take a look at this. Just like yesterday, when you pull up the y equals menu, it doesn't say y equals anymore. At least not in total. It says x equals and y equals. So this is x1, y1. So this is the first set of parametric equations. I happened to be doing this last time, so I'm going to clear this off. I'm going to put in the equation for x. So that's going to be 150 square root 3, close the parentheses. And again, we're going to hit this button for the variable, but it says x, t, theta, and n. If you're in function mode, it puts an x. If you're in polar mode, it puts a theta. We're in parametric mode, so you hit that button and it hits a t. There's our parameter t. Again, you don't have to use t. That's just what we normally use. Any questions? I suppose on the calculator you do have to use t. And then let's put this one in. Negative 16t squared plus 150t and then plus 5. Any questions? Okay, is anybody in here an archer? Shoot crossbows or anything? Okay, hit the window. Okay, what does t stand for in this problem again? Time. This means we're going to start with time equals 0. Does that sound okay? Start our stopwatch. Do we need to go to 45 seconds? Is this arrow going to be in the air for 45 seconds? No, probably not. Let's make it a little bit smaller. Now, we are taking somewhat of a guess. Let's guess 10 seconds. I mean, if something's in the air for 10 seconds, that's a long, long time. Okay? What would the t step do? It's going to do Caitlin's job. It's going to count every second. Now, do we want to know where it is every second, or do we want to know more often than that? Yeah, probably more often. Let's go every quarter of a second. Once we get a graph here, maybe we'll set it up and figure something else out. Okay, so that's a decent guess right now. Now, what does x stand for in this problem? We got an archer standing there. He's going to shoot an arrow like this. What does x stand for? That's the horizontal distance, right? So where should we start? Probably start at 0. So let's put a 0 there. This was in feet. He launched it at 300 feet per second. If we give it 10 seconds and it didn't slow down at all, I mean, that would go like 3,000 feet, right? Okay, so let's maybe guess that. Let's guess 3,000 feet. We don't want a tick mark every foot. We don't want 3,000 tick marks from left to right. So let's put about every 100. What does y represent in this problem? The height. Now, do we need a negative? Okay, probably not. I'm going to come back here in a minute. I am going to make that negative, but let's start with 0. Now, if it's going 300 feet per second and we launch it like this, it's going to go pretty far up before it starts to come down, isn't it? So does somebody want to throw out a guess? 100 feet? 100 feet sounds like a reasonable guess. Let's put tick marks every 25. You ready? Okay, watch. Hit graph. Went up, came down. Okay? Now we went from 0 to 3,000, so that looks okay, but we definitely didn't go high enough. So let's go back here and let's change a couple things. Okay, I'm going to put a negative 100 here. That's going to allow me to see the y-axis. I'm okay with the 3,000. I'm going to put a negative 50 here, and we may end up changing that. It went quite a ways up there. I'm going to go 500, and let's see what we end up with there. And I'm also going to make it calculate more often. I'm going to make it calculate every 1/10 of a second. When we did this in the polar form, what did that do when I made it calculate more often? Made the shape more defined and it slowed it down. There's the arrow going up. And there it is coming down, and I just noticed something. I don't have my axes on here. There we go. Is that a decent sketch? Okay, you don't have to do this, just watch. I'm going to go 0.25. I'm going to have it graph it. It's going to do it a lot faster. And I'm going to hit trace. And look what we've got here. You've got 3 pieces of information down at the bottom. After 2¼ seconds, it's 584 feet downwind or down course, and it's 261 feet in the air. And you can just check the progress every quarter of a second. Now, that's 36. That gives us a sketch of the graph. You could label a couple points on here. Look at number 36. If the arrow strikes the target at a height of 5 feet, how far is the target from the archer? Which equation is that about? Is it about x or y? Okay, it's a question about x. It's a question about how far away is it. But can you just solve that directly? No. In order to know how far away it is, you have to know how long it was in the air. If it hits a target that's 5 feet off the ground, the same height at which it was launched, how could we figure out how long it took to get there? We've got to solve one of these for t. If I set the height equal to 5, and I solved that for t, that would tell me when it hits here. It would actually give me 2 answers for time. You solve that, it'll be very clear which one's the answer, and it'll be very clear which one you plug into here to figure out how far away the target is. Okay? All right, I kept you over. I'll let you go a little early on Monday. Please have the review done, or excuse me, download the review from the website. Have the quiz done when you walk into class on Monday. If you don't, that's going to make life a heck of a lot more difficult. Okay? Have a good weekend.